Foundation Models for Embodied Decision-Making Agents, Part 17. I'm discussing Dieter Fox and then also a paper about masked autoencoders for autonomous driving using video and transformer training for video for autonomous driving. So let's talk about Dieter Fox first. I think Dieter, he's head of research at NVIDIA, so he has this dual role, professor at UW and also head of research at NVIDIA. And I think what's most interesting about this presentation to me is sort of the way he meanders around the problem of robotics and transformers or foundation models. Let's call them foundation models. What's the idea of a foundation model? The idea of a foundation model is to have, as the name says, a foundation. So something that you can build on, let's say a pre-trained model. You want to represent reality as good as you can, and then use that in simulation, ideally in simulation, to train robots. I think this is where the talk actually culminates. Now, he's not formulating it this way. And I think one of the takeaways I have from the talk is that I feel like Dieter, he has a conclusion. I think he knows what he wants, but he also has to represent his work. And unfortunately for academics, let's say what you started 3 years ago might be outdated today. I think Dieter wants to do simulation. I think he wants to solve the inverse problem of going from 3D to 2D, of representing physics by data end-to-end learned. I think that's his goal. But he also has to represent his research that he did. And sometimes that sounds a little bit, maybe almost redundant. But anyway, that's, there's a lot of institutional bias with academics. But overall, I think that, I'm echoing Jitendra Malik here also. I think the robotics community is converging towards end-to-end learned simulation. So real data, embedded simulation, Gen AI to generate multiple versions of objects and actions and then train tasks on that. This is where the community is converging. And then the next step is build an internet of robot actions and have that as a base, feed that back into a transformer-based architecture so you can build kind of like a GPT for robotics. I think that's the idea. I guess two fundamental ideas that NVIDIA is sharing with the world. I think one is parallelism, which kind of comes implicitly with simulation, right? If you have simulation, that's one thing, but then you still have to implement parallelism. And training parallelism is actually in itself quite a challenge. How do you actually, let's say you have a good representation of reality, you still have to find a way to parallelize the training. Excuse me, you have to make it GPU trainable. You have to have a universal scene descriptor, for example, that works with that you can modularize, so you can have, let's say, 50,000 hammers and 50,000 grips that grasp the hammer and use it to hammer a nail into the wall. And you have different types of generalizations and different types of parallelizations while doing this. So those are the kinds of things that Dieter Fox is working on. So on the one hand, applying ideas of robotics to the NVIDIA stack, which is primarily driven, of course, by parallelization. So parallelization, again, data parallelism, model parallelism, pipeline parallelism, all these parallelisms that generally, AI is obsessed about because of the ability to train faster and more efficiently. So one, again, is parallelism, exploit parallelism. And then the other is the simulation pipeline. I think robotics, in my opinion, is becoming a simulation problem. And the simulation is really a representation problem. So it's the question, how do you represent what you see in the best possible way so a robot can learn. And whether you can do a fully 3D to 2D inverse graphics solution, which is have a hammer represented in a way that you can grasp its physics and understand its inertia and gravity, and have all of these things implicitly represented through data, or you have it explicitly implemented into the model through heuristics or even hard-coded. That's still an open question. I think Dieter is not clear about that. I think he's pretty vague about these things, and I think that's probably the culture at NVIDIA right now. It's not clear whether we should go fully end-to-end or we should use physics heuristics. Okay, let's lean back for a second. What is physics? Okay, physics is a representation of the laws of nature and its application. We have a ton of math, a ton of representations, mainly in math language, about physics, going back all the way to Galileo. We're trying to mathematically define what objects are doing, how they're moving, and where they are. Position and momentum, the two fundamental items that physics is trying to explain. Now we could also flip this around and think about physics as the thing that the hammer does. If you take a hammer in your hand and you hit a nail with it, certain things happen. That's what physics is. We don't really care about the mathematics behind. In fact, do we really care about it? Now there's, I think, a cultural tension between old school and new school. Old school is, look, we don't want to throw away all the knowledge that we have. Yes, but do we really need it? Is it maybe even inhibiting us? I just attended a lecture in the transformer class by a gentleman who is a computational linguist. And he's asking the same question. Should we use the knowledge that we have about language to enhance the training of language models? And the answer is probably not. Yes, but we can make it more efficient. I think every time we use explicit knowledge in modeling the real world, it's a shortcut. Isn't the best way to learn about the real world the way we learned it, which is when we go way back, we came from bacteria and evolved into Homo sapiens and so on and so forth. Didn't we just learn by analyzing data? And then we started building representations, hierarchical representations. Yes, we did that. And it helped us. But we have a technology now available to us, which is parallel computing, which helps us analyze a lot more data much faster. And we're going to get much better with computation, talk quantum computing and things like that. So we're going to be able to actually do really, really fast, efficient computation. So why don't we just focus on getting the right data and the right data pipeline and then train? That's just sort of, that's an idea. I'm not propagating one or the other, but my gut's telling me that this is where things are going. And this is how we should tackle this problem of physics and representation in robotics. Actually, Dieter makes an interesting comment. He says that if we want to go down the route of transformers for robotics, there's two ways to do this. One is we could represent the world kind of like in a GPT way, pre-train on, have a representation of the world, use Gen AI to generate more objects and more scenes, and then have robots learn tasks based on that in sim. Or we could actually use robot actions, so kind of an RT2 type model where we look at the ARM farm at Google and things like that, real robot actions, and then we film that, tokenize that, learn from that. So this is really interesting. So there are two ways to tackle the robotics problem from a transformer perspective, right? One is you represent the real world through Gen AI, and then learn tasks based on that, or you actually have real world robot actions and you tokenize those and you learn from that. So that's really important. What does that mean? When I say represent reality, what do I mean? Like what does data actually mean? Well, think about it this way. Like you can film a person holding a hammer and hitting a nail with a hammer. And you can do that in a video, and you capture enough videos about a hammer. And then you use Gen AI to produce even more videos with that hammer. And the idea is that eventually the AI will be really good at capturing the physics of the hammer without any explicit physics being represented in the model. This is the idea. Like think about, let's say, what Hot said about AlphaGo Zero. Now is running Comma AI. And he said, look, would you have trained AlphaGo Zero by giving it specific situations in chess with the queen and the other figures of the chess board, and each position, each specific situation has certain solutions, and you train that sort of one after the other? Or would you do end-to-end the way AlphaGo Zero was trained? Obviously, it's the latter one. That's how AlphaGo Zero was trained. It was trained end-to-end with Q-learning. That means it was trained through self-play. It had the opportunity to profit from a reward function that slowly guided it through variational inference towards a solution which ended up in winning the game on this front. But his conclusion in the end of the talk is actually, he ends the talk with represent reality, generate more versions of reality through Gen AI, and then have robots execute tasks within that reality. We have the semantics for this. We have the large language models which can give robots semantics. You can put a robot in a virtual room and then tell the robot, I want this room to be clean. And then have Gen AI continuously dirty the room, make a mess, and then have the robot fix the mess. That's one option. So I think we have the tools for this. Now we have to all put it together, and it's happening. The other paper I wanted to discuss is this paper. It came out of China on arXiv. I'm going to put the link in the show notes. The paper is about a 4-dimensional masked autoencoder for video for autonomous driving. So the idea is that you use a masked autoencoder, which is the fundamental training technique that transformers are based on. So if we go in the world of text, we take a text, and then we mask some parts of that text, and then we train the model to predict that masked part, and have a loss function that is minimized when the actual prediction corresponds to roughly what was masked. The same can be done with pictures, objects from in 3D, and then you can add a time dimension. That's why it's a 4-dimensional masked autoencoder, and you can have the same architecture with attention blocks and things along those lines. And the idea being that you don't just capture, let's say, objects in a picture, but you capture the relationships between those objects and the temporal relationships in those objects. So you have spatial relationships and temporal relationships, and that serves as a pre-trained model for autonomous driving. This is the idea. I'm incredibly curious to see where Tesla stands on that front. I can't wait to go to CVPR to discuss these things with hopefully Tesla professionals and other professionals. Again, this is related to Dieter Fox. I think it's interesting to ask the question of how much end-to-end learning we can actually do in robotics, or how much we should do, or even whether we should have any heuristics or not. I think those are really fundamental questions. And in my opinion, the answer is as little heuristics as possible, end-to-end, represent reality with real objects, pictures, and then use Gen AI to generate more versions of reality, and then train the robots based on that. The big question, of course, is can we represent physics also? That is an open question, an open problem. According to Jitendra Malik, it's going to be solved. He's confident about it. This is one of the prerequisites to go from physics modeling towards end-to-end training. Thank you.